Hello and welcome to video 2.3 on work, energy, and power. We will only be covering work and energy in this video. Power will be covered later on. So as usual, we are starting with the slide with the data booklet reference. So make sure your data booklet is in front of you. Notice that there are 6 formulas here, but the bottom 2, we're not going to be using those. Okay? So we'll be using those later on. So the formula for power and the formulas for efficiency. So going here for a moment. We are doing 2.3 right now. So last time we covered 2.2. So 2.3, we're in this bottom left box right here. We are only going to be covering the formula on the top. So W, the next one for EK, the next one for EP, and then that next one for delta EP. These ones we'll cover later on. So we'll get to them, but not right now. Okay, let's go back to the slides. So this is the IB stuff. So we're just going to pass this. Okay. Work done by a force. So up till this point, we've been looking a lot at Newton's laws, specifically Newton's second law, F net equals ma. And looking at a scenario, we've been drawing free body diagrams and using Newton's second law to solve them, solve the problems. And it's been working quite well, actually. Now, sometimes you can't use Newton's laws to solve a problem. And sometimes when you can, it's just easier to solve it from an energy perspective. So before we get to energy, we first have to talk about work. So a weakness with the second law is that you have to know all of the applied forces in order to solve the problem. So let's look at the next slide here. Imagine this scenario. You have a ball at the start of this ramp, and it's going to roll down this ramp until it hits or goes into the cup. All right, so discuss the problems in using free body diagrams to find the final speed. Well, when we use free body diagrams, we're essentially trying to look at all the forces acting on the ball at various points throughout its journey. So if you look at the ball at various points, you can see that the weight always has the same magnitude in the same direction, down, but the normal force keeps changing its direction. And if the normal force keeps changing its direction, and that's because the ramp is changing direction, that means that the net force is also changing. If the net force changes, that means acceleration is changing. And so we don't deal with changing acceleration in our dynamics equations, and we don't look at those kinds of problems. Using Newton's laws, I should say. We are going to look at these problems, but from a different point of view, and that is the point of view of work and energy. So we can't solve this using the kinematics equations. Okay. So we are going to define something used commonly in physics called work. Now, work defined in physics is not what you might think of work as. There's a lot of terms used in physics that are not defined based on how you know them to be defined, based on your daily life. For example, we learned that weight is not what the scale reads when you stand on it. We now understand that when you stand on a scale, it is reading to you the normal force, which is why when you're in an elevator and you're accelerating up or down, your scale is going to read something different. Either you're going to be heavier or you're going to be lighter. Right? So in physics, you could be sitting at your desk doing homework for 45 minutes, and physics would say you have done no work. Why is that? Okay. In the definition of work by physics, work is force times displacement. So if you have a displacement of 0, as you would if you were sitting in one spot doing your homework for 45 minutes, therefore your work would be 0. So it's a slightly different definition of work than you're used to, but nonetheless, it's not too bad. So work by a constant force. Now, if we look at the units, force is measured in newtons. S, remember, is distance. That's measured in meters. So we have a Newton meter for work. But instead of saying a Newton meter, we just abbreviate that and call it joules. Okay, so J, in honor of the physicist by that name. Okay, example. Find the work done by the 25 Newton force F in displacing the box 15 meters. Okay, so there's my box. The force is applied and it gets displaced 15 meters. So let's find the work done. Okay, so switching screens here. Example. Okay, so we're looking for work, W. I guess this can also get confusing because W can represent weight. You have to just make sure you keep track of it. Okay, W also represents work. Actually, something I'll point out, a big difference between work and weight is that weight is a vector and work is a scalar quantity. So let me just actually write that here. Work is a scalar, which means it only has magnitude, it doesn't have direction. and we know that it's measured in joules, which is equivalent to Newton meter. Okay. Right, so we're looking for work. We know the force is 25 newtons, and we know that it's being displaced 15 meters. Okay, analysis, work is equal to force times displacement, which is 25 times 15. Grab your calculator. 375. 375 joules. Again, if you want, you can call that 375 nanometers. Nothing wrong with that. Let's go back to the slides, and there's that same solution. In the slides, it's 380 because this is taking into account sig figs. All right. Now, there is a more correct formula to use. The formula W is equal to Fs is not wrong, but that's only for a specific case, and the case is when the force and the displacement are in the same direction. Now, oftentimes the force and the displacement will not only not be in the same direction, but they're often at some angle to each other. So this is the proper equation for work, and this is the first equation in box 2.3 in your data booklet. W equals Fs cos theta. Now it says here theta is the angle between F and S. Specifically, it's the angle when they're placed tail to tail. Okay, and we'll do some problems with that. There's a couple things to point out. Because it's dependent on cosine of theta, cosine changes values. All right, so if you know what the graph of cosine of theta looks like, then you'll understand how work will change based on the angle between F and S. Chances are, since you're in grade 11, unless you have taken grade 11 math already, you wouldn't know what the graph of cosine theta looks like. Let's just go back for a moment. I'm going to really quickly sketch it, but we'll look at this in much more detail later. But for now, let this just be enough. If we plot cosine theta versus theta, it actually looks something like this. Okay, so the maximum y value is 1, the minimum y value is -1, and it ranges from 0 to 360 degrees. So this low point here is 180 degrees. It crosses here at 270, and it crosses here at 90 degrees. So that's what the graph of cosine of theta looks like. So depending on the angle theta between F and S, by the way, F and S have to be tail to tail. So if this is S and this is F, this angle here might be 120 degrees. So where's 120 degrees? 120 might be somewhere like this. So we can see here that the ratio of cosine theta, when theta is 120 degrees, is negative. So that means I would end up with negative work. We'll talk all about negative work, positive work, cosine of theta more over the next couple of slides. Okay, but these are special cases. If F and S are parallel means, well, they're going in the same direction. Theta is 0, but cosine of 0 is 1, and you can verify that on your calculator. If F and S are anti-parallel, then theta is 180 degrees, and cosine of 180 is -1, in which case you would have positive work and then negative work. Anti-parallel is a bit of a difficult word because technically speaking, if two things are parallel, they could be going in the same direction or opposite by definition. In physics, if they're parallel, and even sometimes in math, if they're parallel, especially for work, assume they're going in the same direction. If they're anti-parallel, opposite directions. Okay. Practice. Find the work done by the force 25 newtons in displacing a box 15 meters if the force and displacement are A, parallel, B, anti-parallel, and C, at a 30-degree angle. So we've already pretty much done this for part A. Okay, this is part A, right? So if you have the formula work is equal to Fs cos theta, if they're parallel, theta is equal to 0 degrees. And cosine of 0, if you don't believe me, grab your calculator. Cosine of 0 is 1. Okay, so then it just becomes F times S, which is going to be 375 joules. So this is effectively the answer to A. B, anti-parallel, so that means theta is 180 degrees. So that means you have F going like this, and you have S going like this. Okay, so the formula is work is equal to Fs cos theta. Force is 25, displacement is 15, cosine of 180. Based on this graph, we can see that when theta is 180 degrees, the y value is going to be -1. So cosine of 180 is -1, but I'll just stick it there just so you can see. So minus 375. Okay, so we get negative work like that. Let's do part C, and at a 30-degree angle, so this time we have something like this. So we have the force and we have the displacement, 30 degrees between them. So W is equal to Fs cos theta, which is equal to 25 times 15 times cosine of 30 degrees. 25 times 15 times cosine of 30. 325 joules. So less than we had before. So something interesting to point out, sometimes we have positive work and sometimes we have negative work. This is the maximum work we can have. So the maximum work that you can do on an object is when the force and the displacement are in the same direction. And if you're at some angle that's not parallel, you're going to get less than the maximum amount of work. And you think about, well, okay, maybe not thinking about opening a door, but think about moving a box across a flat surface, like a floor. Okay, if you're trying to move a heavy box across the floor, you're going to apply some force onto it. Okay, so imagine this is you pushing the box towards the right. You want the displacement to be to the right, and certainly if you push the box, that's the way it's going to move. And if you apply your force in the same direction as the displacement, you're going to have the most efficient transfer of energy. If, however, you apply your force down or you apply your force up, you know that that's not going to be as efficient, and only some of your energy will actually go into displacing the box forward. So you're not doing much work on the box. So the most work is done when these two things are in the same direction. Let's go back to the slides. Okay. Find the work done by the brakes in bringing a 730 kilogram smart car to a rest in 80 meters if its starting speed is 32 meters per second. All right, so let's go back to the paper. Let's solve this problem. Okay. So example. So we're looking for the work done. Now this car is coming to a stop, so we've got a smart car here. Can't imagine what it must feel like to drive one of these next to a transport truck on the highway in the winter when there's ice on the highway. God, that would be scary. If the starting speed is 32 meters per second, final velocity is 0 because we're bringing it to a rest. This occurs over a distance of 80 meters. And the mass of the smart car is 730 kilograms. If you remember, we did a problem in an earlier video where there was an airplane that was 1,000 kilograms, and I said that's pretty light because there's a lot of cars that weigh 1,000 kilograms, and now you can see that makes sense. Just a smart car weighs 730 kilograms, so just a regular car will easily weigh 1,000 kilograms. Excuse me. Okay, find the work done by the brakes. So work we know is equal to force times displacement times cosine of theta. Now we're looking for the work done by the brakes. So if you were to look at a free body diagram of the smart car, let's look at the forces acting on it. We've got its weight going down. We've got the normal force going up. Now technically the normal force is coming from each tire, but we'll just draw this as one force right now. If you're braking, there's no thrust going forward, or I guess gas or fuel source of force going forward, but you do have friction going back. So we have force of friction. Friction is going backwards, but the car is being displaced forwards. So look at that. What is the angle between force and displacement? If you said 180 degrees, you are correct. Right? When you place them tail to tail, that is 180 degrees between them. And sure enough, cosine of 180 degrees is -1. At some point, you're just going to memorize these, right? So you can always check that in a calculator if you're not sure. So I can already see that I'm doing negative work on the car. All right, so force times displacement. Now, I know what the displacement is. It's 80 meters, so I got to figure out the force. Well, looking at the diagram, in the x direction, I only have one force, and that's force of friction. So in my x direction, that's my net force. So I'm going to actually define my positive and negative x directions. Because I'm accelerating to the left, and that has to be the case if I'm slowing down. I'm going to let left be my positive x direction and up be my positive y direction. Okay, so that means if I have F is equal to the sum of the forces in the x direction, that's after all what it is, and that is going to be equal to the frictional force, and specifically it's the dynamic friction because the car is in motion. Now, dynamic friction, there's a couple ways I can do this. I can either look at my formula sheet and say, well, okay, I can calculate dynamic friction by saying it's mu d times r, so the coefficient of dynamic friction times the reactive force, but I don't have mu, I don't have the coefficient of friction. So understanding that it's the net force, I can set that equal to mass times acceleration. Okay, so mass I know, and acceleration I can find. I have u, v, and s. Okay, so now we have to go back to our dynamics for a moment here. U, v, s, and a. So I can use v squared equals u squared plus 2as. Okay, so v is 0. 0 squared is 0. So that's 0 equals u squared plus 2as. We're isolating for a, so let's bring the negative 2as to the left. Equals u squared. Now divide both sides by negative 2s. So a equals negative u squared over 2s. All right, so negative u is 32, so 32 squared. The squared is only being applied to the 32, by the way, not the negative. Divided by 2 times 80. So 32 squared divided by, well, 2 times 80 is 160. So what is that? That's 6.4. Okay. And that's going to be actually negative 6.4. Right. Oh, something I should point out, actually. Since I defined left to be positive x, that means the displacement's actually in the negative direction. So this is actually negative 80, which makes negative and negative positive. Okay, that makes more sense. Since acceleration is going left, and I define left to be positive. Okay, so we've got acceleration 6.4 meters per second squared. That gets plugged in over here. Okay, so that means m times a, which is equal to f. That's going to be 730 times 6.4. So 6.4 times 730. What is that? 4672 newtons. Okay, so there's my force. Now that gets plugged in back over here. So work is equal to 4672 times 80 times negative 1. Now, if you're wondering why I didn't make this negative, is because I already took into account the direction by putting the cosine of theta here. So the minus 1 already takes account for that. So 4672 times 80, oh, that's a big number. 373, and we have to put the minus in front, minus 373, 760. And you can put the units as Newton meters or joules. I'm going to put joules. Okay, so therefore the work done by the brakes in bringing the car to a rest is negative 373,760 joules. So what I really want you to notice and keep in mind, because we're going to come back to this, is that in order for the speed to decrease, negative work had to be done. I'll say that again. In order for the speed to decrease, negative work had to be done. So just keep that in mind. We'll come back to this later on in the lesson. Okay, next. A pulley system is used to raise a 100 Newton crate 4 meters as shown. Find the work done by the tension force T if the lift occurs at constant speed. Okay, so we've got a pulley system. The reason we have pulleys is a pulley is an example of what's called a simple machine in engineering, and it's used to redirect force. So instead of having to pull up on something, you can pull down. And sometimes pulling down is easier than pulling up. All right, so the crate is 100 newtons. That's its weight. Okay, we have to move it 4 meters. What is the work done by the tension force? Now it's occurring at constant speed. Let's go back to our page here. Okay, so we've got a pulley, and it's bringing up this box because a tension force is being applied. Okay, now the crate is 100 newtons, and we're displacing it 4 meters. Now, if the crate weighs 100 newtons, so if you were to look at a free body diagram of the crate, it has weight and there's a tension force going up. But that tension force is also getting redirected and being pulled down. So whatever the tension force is here, that's the same tension force here due to an example we saw, one of the worked examples from the previous section. Because it's the same rope, it's the same tension force. So looking at this, if it's going up at constant speed, that means acceleration is 0, therefore the net force is 0. And if the net force is 0, that means if there's only one force going up and one force going down, they have to equal each other. So T is equal to W. And so tension is equal to 100 newtons as well. So if we're looking for the work done by the tension force, well, that's going to be equal to the tension force times the displacement times cosine of theta. Okay, so tension force is 100, displacement is 4 meters. Now to figure out the angle, we have to see, well, which way it's going. So find the work done by the tension force if the lift occurs at constant speed. So you know what, we'll keep this, because it's the tension force due to the lift, that means theta is going to be 0 degrees and cosine of 0 is 1. So we'll just stick a 1 in there. So 100 times 4 is 400. That's 400 joules. So therefore 400 joules of work is done by the tension force when the lift occurs at constant speed. Let's go back to the slides. Okay. We are going to skip this next slide, so go ahead and just cross it out. You don't need to worry about this. So again, cross this out. Okay, now let's start talking about energy. So we talked about work, now energy. Well, in order to talk about energy, we have to first explore different types of energies. And there are two main types that we're going to be looking at in grade 11, kinetic energy and gravitational potential energy. Okay, so kinetic energy, abbreviated with the symbol E sub k, is the energy of motion. So if an object has speed, it has kinetic energy. The more speed it has, the more kinetic energy it has. Okay? Other things that control kinetic energy, mass. If an object has more mass, it has more kinetic energy. Okay, so here's the formula for kinetic energy, 1/2 mv squared. And that is the second formula in box 2.3 in your data booklets. Okay, now the units for kinetic energy, if you'd like, you can go through this unit derivation on the slides, but suffice it to say, the unit for all types of energies is the joule, J. Now we've seen that before. Joule was also the unit given to work, and there is a very close relationship between work and energy, which we will see soon. Something to note, many books use the symbol capital K instead of EK for kinetic energy. I've even seen capital KE for kinetic energy. Honestly, every book uses different symbols. Okay, so this book uses one set of symbols. Nelson uses another. There's another book called Giancoli, that's AP Physics. They use another set of symbols. In university, you will use another set of symbols. If you take the OAPT physics contest, they will use another set of symbols. It gets annoying, but they all represent the same thing, and it's something that you will eventually get used to. Okay, let's try this problem. What is the kinetic energy of a 4-gram NATO SS-109 bullet traveling at 950 meters per second? So that's a nice close-up shot of the bullet going through an apple. That's quite remarkable. Okay, let's go to the page and solve this problem. So we're looking at kinetic energy. Okay. So EK is equal to question mark. Mass is 4 grams. It's traveling at a speed v of 950 meters per second. And I know the formula for kinetic energy is 1/2 mv squared. Something to keep in mind, don't just go and plug those numbers in. Whenever you use a formula in physics, every quantity that you plug in has to be an SI unit. Now, V is already in the SI units of meters per second, but mass is not. The SI unit for mass is kilograms. Now, to go from grams to kilograms, I have to divide by 1,000. Imagine you had 4 meters and you want to express how many kilometers that is. You know that this number has to get smaller, right? So we're going to divide by 1,000, or you could write it as 4.0 times 10 to the minus 3 kilograms. How did I know to do that? Well, some of you might just be familiar with the prefix kilo, and if you're not, take your data booklet, and under metric multipliers, if you look at kilo, it's the fifth one down from the top. It says times 10 to the 3, right? But if you're going backwards, right? So if you're making the number smaller, you're not multiplying by 10 to the 3, you're dividing by 10 to the 3. So it's actually times 10 to the minus 3, right? If you multiply by 10 to the 3, that means you're multiplying by 1,000, which is going to make it bigger. That doesn't make sense. Excuse me. So here we go. 1/2 m, so 4.0 times 10 to the minus 3, times v, 950 squared. So not to worry, because the speed will more than make up for that tiny mass. 1/2 m. Oh, by the way, I haven't shown any of you this yet. Whenever you have some number times 10 to the something, and you're going to have a ton of these, whenever you have something in scientific notation, if you have a Casio calculator, I mean, it's going to be the exact same button. But if you don't, you probably have a similar button. Mine says EXP on it. So if I press EXP, notice that the letter E comes up. And what I do is, after the letter E, whatever exponent I have here on the 10, I stick that after the E. So because the exponent here is -3, I put -3. So 4e minus 3 means 4 times 10 to the minus 3. Okay? So there's that number. So 4e minus 3 times 950 squared. So what is that? That's 1805. 1805 joules. Okay, I gotta point this out. Energy is a scalar, just like work. Okay, so let me just write that here so you have it. Energy is a scalar quantity. It only has magnitude. Now, while scalar quantities can be positive or negative, energy is always positive, but work, it can be positive or it can be negative. Okay? Although they're both scalars, there's a reason why energy can't be negative. It just doesn't make sense for you to have negative energy. It doesn't work. Work, on the other hand, can be negative, and we'll understand why that is in a couple slides. Okay, so here we have 1800, again rounding for sig figs. All right, what is the kinetic energy of a 220-pound NATO soldier running at 6 meters per second? So this soldier has much more mass, but they are running and they're moving much, much slower. Now, I'm not going to ever give you pounds without giving you the conversion, so we'll just look at the conversion first. So 220 pounds is 100 kilograms. Let's go back to the work here. So we have a mass of 100 kilograms. They're running at 6 meters per second, and I need to find the kinetic energy. So kinetic energy is 1/2 mv squared, which is 1/2 times 100 times 6 squared. So grab your calculator. Half of 100 is 50, so 50 times 6 squared is 1800. And keep in mind, this is rounding for sig figs. So in fact, these two numbers really are the same. This number here, however this was rounded to get 100 kilograms, well, that means the conversion is a little bit off, but that's okay. But the fact of the matter is, you can have something really, really tiny like a bullet have the same kinetic energy as a person, as long as the tiny thing is moving really fast and the big thing is moving really slow. Back to the slides. Okay. Now, work as energy transfer. Watch this derivation. It's actually very interesting. Okay, so starting off with this kinematic formula, v squared equals u squared plus 2as. The first thing I'm going to do is multiply both sides by mass. Okay, so you have m on the left, m on the right. You haven't changed anything because what you did to the left, you did to the right. Okay, next, take that mass and distribute it on the right side. So m times u squared and then plus m times 2as. Now, of course, they put the 2 in front. That's fine. Next, ma appears in this last term. Now, I know that the product of mass and acceleration is equal to force, specifically net force. So I replace that with F. Okay, Next thing I'm going to do, I'm going to multiply everything by 1/2. Okay, so I have 1/2 mv squared, 1/2 mu squared, and then the half times 2 becomes 1 and it disappears. I hope this is starting to look familiar to you. I know that 1/2 mv squared is kinetic energy, but then what would 1/2 mu squared be? Well, if u is initial speed and v is final speed, then it would make sense that this is the final kinetic energy and this would be the initial kinetic energy. Now, what about F times S? F times S is work. So final kinetic energy equals initial kinetic energy plus work, or written another way, work is equal to final kinetic energy minus initial, or work is equal to delta EK. This is a remarkable consequence of this, well, manipulating the original formula. That's called the work kinetic energy theorem. And unfortunately, it is not in your data booklet. So please, please, please memorize this formula. You do not at any time ever need to derive this formula. If you want to use it in a problem, you just state this exactly as is. W is equal to delta EK and move from there. I'll show you a question in which it can be used. Now this problem should look familiar because we just did it. Okay, it was the second, well, rather third example that we did today. So we have a smart car, 730 kilograms. We want to bring it to a rest in 80 meters and its starting speed is 32 meters per second. I just want to show you the original solution that we did. I mean, it took us quite some time. We knew that work was equal to Fs cos theta. We realized that theta was equal to 180, so cosine of 180 was -1. S is 80, but then we had to figure out the force. So then we said, okay, well, force is equal to mass times acceleration, and so then we had to find the acceleration. So then we used a kinematics expression and solved for acceleration. Plug that back in here, found the force. Plug that back in here, found the work. It was a long problem, no doubt. Now you're going to see how the work kinetic energy theorem is going to solve that problem in less than half the time. All right, so mass, 730 kilograms. This thing is initially traveling at 32 meters per second, and it eventually reaches a speed of 0, and it does this in 80 meters. Okay, use the work done by the brakes. So we're looking for W. Well, because its kinetic energy changed due to work done by the brakes, work is equal to delta EK. Oh, I'm sorry, guys. Work is equal to delta EK. So that's final kinetic energy minus initial kinetic energy. Some people put 0 for initial, and we pronounce that not. And some people just put an I for initial. That's up to you. So that's 1/2 mv squared minus 1/2 mu squared. Now v is 0. So v squared is 0, and 0 times anything is 0. So this whole thing is gone. So that means minus 1/2 m, which is 730, times u squared. So 32 squared. So negative 0.5 times 730 times 32 squared. That's minus 373,760 joules. And sure enough, if we grab our original solution, there it is, minus 373,760 and minus 373,760. So we get the same answer, but in a lot less time and much easier. A lot of problems you can actually solve using Newton's laws and work, or you can use the work kinetic energy theorem, or as we'll see later on, conservation of energy, which is really nice. And a lot of times the energy method solves the question much faster and more efficiently than using Newton's laws, although that method still also works. All right, back to the slides. All right, so we talked about kinetic energy, the energy of motion. If an object has mass and it has velocity, it has kinetic energy. The other main type of energy we're going to look at this year is gravitational potential energy. All right, so consider a bowling ball. A bowling ball is pretty massive. If you leave a bowling ball on the floor, it will stay there. It's not going to move. But if you raise it to a certain height, delta H, and then you let it go, it will fall. And as it falls, it speeds up. Okay, so as it falls, it gains kinetic energy. Now, because lifting it means you have to go against gravity, hence why heavier things are harder to lift, and lifting things to higher heights is more difficult, that means you're doing work on the bowling ball as you're lifting it. And that work is equal to F times S times cos theta. The force that you're trying to overcome is the force of gravity. That's the weight. And we know that weight is equal to mg. Okay, so F is equal to mg. We're raising it through a height delta h. And the angle between those two is going to be 0 degrees. The force that you apply is going up. So that's F, correct? And delta h is going up as well. So the angle between those two is 0. So the work is mg delta h. And this is what we call gravitational potential energy. When an object is elevated at a certain height above a certain reference point, we say that there is energy stored inside of it. We say that this object now has the potential to gain speed as it decreases in height, okay, and it gains kinetic energy. Let's do this problem. Consider a crane which lifts a 2,000 kilogram weight 18 meters above its original resting place. What is the change in gravitational potential energy of the weight? Okay, so let's do this problem. So the crane is lifting a 2,000 kilogram weight. So mass is 2,000 kilograms, 18 meters above the original resting place. So you have some kind of a crate and it's being lifted 18 meters. So at some point it's going to be over here. Okay. What is the change in gravitational potential energy of the weight? So delta EP. Now some books call this delta EG for gravitational potential energy. Now, it is a type of potential energy, so some books put P, and we'll use P. There are other types of potential energies, but for now, we're just going to study gravitational potential energy. All right, so delta EP is equal to question mark. Well, if we call the original height that this crate was at 0, then that means it increased to another height over here, and that's going to be h is equal to 18 meters. So this is h1, that's h2. Hence, delta H is 18 meters, right? H2 minus H1. Now I know that the change in potential energy is equal to mass times the acceleration due to gravity times the change in height. So mass is 2,000 kilograms. I know G is 9.8 newtons per kilogram, and delta H is 18 meters. So plugging all that in, 2,000 times 9.8 times 18. So we get 352,800 joules. So something interesting to point out here is that because the change in potential energy is positive, you automatically know that it gained height. The only way for you to gain potential energy is for you to gain height. Let's go back to the slides. Okay. Oh, something to point out, the reason why it's 360,000 here is because they're using 10 instead of 9.81. Okay. Same crane, same mass, same distance. How much work does the crane do? Okay, so back to this. So now we're looking for work. Well, work is equal to force times displacement times cosine of theta. Well, the force is lifting it up, right? But what is the force trying to counteract? It's trying to counteract gravity, right? So you have this crate and you have a force acting on it up, but it's trying to counteract W. And it's being lifted at constant speed. We can assume this because otherwise the question would become way too complicated. So F is equal to weight. I'm not going to plug it in as W because then you're going to have W is equal to WS cos theta. Too confusing. So I just know that W is equal to mg. So I'm going to replace F with mg. Now, what distance is it being displaced? It's being displaced delta H, 18 meters. So I put delta H here. Now F is going up. The thing is also going up. So the angle between these two vectors is 0 degrees. And cosine of 0 degrees is 1. So that's 1. I don't even need to write it. So mg delta H, well, guess what? That's the formula for change in potential energy. And so this shows us once again that work is equal to change in potential energy. Okay, now work can also equal the change in kinetic energy. Okay, so just keep that in mind. You can only consider one or the other at the same time. Okay, so if we do mg delta h, I have the same expression here. I'm not even going to plug in the numbers because I just did it. I'm going to get the same value here. So 352,800 joules. All right, good. Back to the slides. All right, so now, so the 2,000 kilogram weight is 18 meters above its original resting place. If the cable breaks at the top, find the speed and the kinetic energy of the mass at the instant it reaches the ground. Okay, so now the cable breaks at the top. So this thing is at the top, and the cable breaks and it starts to fall and eventually lands on the ground. So we want to know the speed and the kinetic energy when it hits the ground. So V is equal to question mark. Initial speed is 0 because the cable breaks. That means it was at rest. Now when it's falling due to the influence of gravity. So the acceleration is negative 9.81 meters per second squared. Now the fact that I put a negative there implies that I'm setting up to be positive. Now actually, let me really think about that because this object is also getting displaced down. In fact, it's getting displaced 18 meters down. So if I just actually set down to be my positive direction, I can let this be positive and this be positive. So I don't have to deal with all those negative signs. So I have SUAV. Okay, so the formula that I'm going to use is V squared equals U squared plus 2AS. U is 0, 0 squared is 0. So V equals the square root of 2AS. So square root of 2 times 9.81 times 18. What's that? 353.16. Oh, and I have to square root. 18.8, let's call it. So 18.8 meters per second. So that is the speed when it hits the ground. Now for the kinetic energy. EK is equal to 1/2 mv squared. So 1/2, the mass we were originally given is 2,000 kilograms. So 2,000 times 18.8 squared. $353,440 joules. Now, any difference in number between this and this or this is due to rounding, right? So I rounded this number, let's not forget. So this is why the values could potentially be different. In fact, actually, let's check that out. If we do 2 times 9.81 times 18 equals, and we square root that, we get 18.8. And then if we square that again here, sorry, 18.79255,172, if we square that, and then we multiply by 2,000, and we multiply by 1/2, we get 353,160. Okay, so that's okay. It's a little bit different, but that's okay. And I just realized why, because I have 9.8 here, not 9.81. Okay, so if you guys forgive me, give me a sec. Let me see if I can do this really carefully. Let's make that a 9.8. I really want the numbers to match. 2 times 9.8 times 18 equals, and square root that, 18.78, da da da. If we square it over here, and we multiply it by 2,000, and then we multiply it by 1/2, 352,800. Perfect. Okay, so there's the proof. 352,800 is, so if you don't round, everything's exactly the same. You get the same value here and here. Okay, and that's exactly what you wanted. And so what that shows is that the amount of gravitational potential energy that I have at the top, I have the exact same amount. Okay, so the exact value we just found, and there's the proof, 352. You have the exact same amount of kinetic energy at the bottom. Now that is very, very important. It shows that energy was conserved. It wasn't destroyed. It simply changed from one form to another. Back to the slides. Okay. If the cable breaks at the top, find its change in kinetic energy and change in potential energy at the instant it reaches the ground. Okay. When this thing reaches the ground, we'll think about it like this for a moment. From the ground up, this crate gained 352,800 joules of energy. So if you go from now the top back down to the bottom, it's not going to gain 352,800 joules of energy. It's going to lose that much energy. And even based on the equation, you can see it. M and G would be the same, but now it has a delta H of negative 18. So on the way down, delta EP would actually be negative 352,800 joules. On the other hand, when this crate starts at the top, and I've drawn this here as well, the speed is 0. So its starting kinetic energy is 0, but its starting potential energy is at a max. When it falls, it gains speed, but it loses height. So when it gets to the bottom, it has 0 potential energy, but it has maximum kinetic energy. So that means that the kinetic energy actually gained, so plus 352,800 joules. Now in this circumstance, we're assuming that no energy is being converted to thermal energy due to drag, air resistance, those types of things. Okay, back to the question. All right. If the cable breaks at the top, find the sum of the change in kinetic and the change in potential energies the instant it reaches the ground. Well, we just looked at what is the change in those energies. So let's add them together. If you do delta EP plus delta EK at the same point, so minus 352,800 plus 352,800, we're going to have 0. So the difference in one plus the difference in the other should always be 0. That's important. Okay. So what we essentially saw in the last slide was that energy is always conserved. While it does change from one form to another, it can never be destroyed. Now, even if you account for air resistance and some of the energy becomes heat, that's not violating the law of conservation of energy. That just means that some of the energy happened to become heat, some of the energy became kinetic, while the original energy was gravitational potential. Okay, but energy conservation always takes place. If you have friction and drag, then you just have one more quantity added to this. You would have delta E thermal or something to that end. Now, that statement in the box is known specifically as the conservation of mechanical energy. And the reason for that is what is specifically defined as mechanical energy. So by definition, mechanical energy is the sum of kinetic and potential energies. Okay? So whenever you hear mechanical energy, it means sum of kinetic plus your gravitational potential energy. A really nice way to put all of this is the total energy of a system never changes. Okay, so let's try a problem. Find the speed of the 2-kilogram ball when it reaches the bottom of the 20-meter tall frictionless track. So I hope you have the slides in front of you so that when I solve this problem, you have that image in front of you. I'm just going to quickly sketch it again, but we have something like this. So we have a big dip, and then a not as high hill, and then this thing goes into a cup. And here's your ball. Okay, so originally, so this thing ends up at this height. So we'll call this our reference height, h is equal to 0. Relative to the reference height, it starts at a height of 20 meters. Now for conservation of energy problems, I like to solve them differently than what's in the slides. I just find this method to be really nice, really organized, and just really helpful. So what I do is I pick 2 or more, depending on the question, points to analyze. Now I want to find the speed when it reaches the bottom of the track. And since it's frictionless, whatever speed it has here, it will have the same speed here. Now, based on how roller coasters work, if you've ever been on one, you would know that the roller coaster goes slowest when it's at the highest heights, and it goes fastest when it's at a lower height. Now, I'm talking about the traditional roller coasters, not the ones that suddenly accelerate from the beginning. like Rock and Roller Coaster at Walt Disney World, or Aerosmith's roller coaster, whatever it's called. Or I think there's one in Universal Studios called the Hulk. So it's not a roller coaster that accelerates right away. It's the one that goes up that huge hill and then just kind of lets go and speeds up, slows down, speeds up. And then here it's frictionless, so the speed stays the same. Okay, so mass is 2 kilograms. So what I do is I pick 2 points. I'm going to pick this point, which I'm going to call point 1. I'm going to stick the number right inside the ball there. And I'll call this point down here point 2. But like I said, these 2 points aren't really the same. And I know due to the law of conservation of energy, the total energy of the system at point 1 equals the total energy of the system at point 2. Okay, so that's what ET stands for, total energy. Now, any point that I pick along this path, I know that the total energies will be the same. But I just have to pick my points carefully. So I pick the first and the last. Now, I know the height here, so we're going to call this H1. Now, the ball does start from rest up here, so that's going to be V1 equals to 0. We are trying to find the speed here, so we're looking for V2. And I know H2 here, based on my reference line here, H2 is 0. And usually you have something like this. You have a V1, V2, H1, H2, and you know 3 pieces of information, and you're looking for the 4th. Okay, so at ET1, assume ET1 is made up of potential energy at 1 plus kinetic energy at 1. And ET2, you have potential energy at 2 and kinetic energy at 2. Okay, so potential energy at 1 is mgh1. Kinetic energy at 1 is 1/2 mv1 squared. Potential energy at 2 is mgh2. And kinetic energy at 2 is 1/2 mv2 squared. At some point, you're going to get fast at this. You won't even need to write all of these out. You're simply going to understand that there's no kinetic energy here and there's no potential energy here. Okay? But nonetheless, let's go through the solution for, thoroughly the first time. H2 is 0 and V1 is 0. 0 squared times anything is 0, so this whole thing is gone. And 0 times mg is 0. So we're left with mgh1 equals 1/2 mv2 squared. Okay, so mass gets canceled. Now rearranging for V2, actually I can bring this over here. V2 is equal to, so the 2 gets multiplied first, so 2gh1, and then we square root. Okay, so that's square root of 2 times 9.81 times h1, which is 20. Square root 19.8 approximately meters per second. Okay, so that's the speed of the 2 kilogram ball when it reaches the bottom of the frictionless track. Okay, back to the slides. Okay, this diagram should look very familiar to you. We actually did this same problem in section 2.2 using Newton's laws and free body diagrams and rotated coordinate systems. You still have to understand how to do rotated coordinate systems, although solving this using conservation of energy will be so much simpler. So we have a 25 kilogram object resting on a frictionless incline, and it's released as shown. What is its speed at the bottom? All right, so going back to the page. Okay, so we have our incline, and this is 30 degrees. This height is 6 meters. This thing starts up here, and then it moves down, and eventually it reaches the bottom. So I know here the initial speed is 0. I know the final speed is what I have to look for. I can figure out the distance using SOHCAHTOA, and then all that would be left would be to find the acceleration, which is found using net force, and that's what I did in section 2.2. It works, it's a beautiful solution, but it takes a long time. So why not use conservation of energy? Because I have different heights and I have different speeds. So I'm going to let this be my reference line here. So this will be h is equal to 0, which means that this thing starts at h is equal to 6 meters. H is the height above the ground. So we'll call that h1, and this will be spot 1. This will be location 2. Okay, so according to the conservation of energy, the total energy at location 1 equals the total energy at location 2. And like I said, you can pick any point. I just happened to pick the 2 points that are most useful to me in the problem. Now, I know this thing is released from rest, so V1 is equal to 0. This down here is H2, and I am looking for V2. Since V1 is 0, I know that originally I have no kinetic energy, just potential. So ET1 is just EP1. And ET2, I have no potential energy, just kinetic. It's EK2. So here I have mgh1 equals 1/2 mv2 squared. And you can actually see for this type of a problem, they don't even have to give you the mass because it just cancels out. The reason why you can cancel out the mass here, or even technically up here, is because it appears in every single term. Okay, so you can imagine factoring it out from left and right side and then dividing it out. All right, so we're left with gh1 equals to 1/2 v2 squared. So v2, rearrange, so the 2 goes over first, 2gh1, and then square root. So square root 2 times 9.81 times 6.0. So 2 times 9.81 times 6, square root 10.8. Let's call that. All right. So the speed at the bottom is 10.8 meters per second. So back to the slide. Okay, there we go. Now we have so far talked about kinetic energy, we have talked about potential energy, well, specifically gravitational potential energy. There will be other potential energies. There are so many types of energy, some which we're going to learn how to calculate in grades 11 and 12, and some that we're not even going to get to in high school that you'll learn about in university. There's chemical energy, there's nuclear energy, electrical energy, and magnetic energy. We have sound energy and light energy, and we also have heat energy. Now, really, in grade 11, we're only going to worry about kinetic, potential, and heat. Now, if you're wondering why we didn't see heat yet, it's because heat is just called thermal energy. So, for instance, let me just go back here for a moment. As this block slid down, we assumed that this ramp was frictionless. So there, in other words, after this thing slides down, if you were to pick up the block and feel the bottom of it, it wouldn't feel warm because there's no friction. So no energy was lost due to heat. But we will see a problem where energy gets converted to heat. Okay. Here we go. So similar problem to what we started with. We have the 2 kilogram ball. It's 15 meters per second when it reaches the bottom of the 20-meter tall track. Find the loss of mechanical energy and its location. Okay, so let's go to our page. So we have this scenario. Now this one, when you have heat and loss of energy, it's difficult to use the conservation of energy system that I showed you in the last 2 examples. All right, so I know the mass is 2 kilograms. I know the speed down here is 15 meters per second. So V2, I'll call it V2, 15 meters per second. 20-meter tall, so this is H1, 20 meters. V1 is 0, so we'll call this location 1, location 2. And H2 is 0 meters. Okay. Normally, we would set these two equal to each other, but now we're assuming that there is friction here, and so there's some energy loss due to heat. So if you only consider there to be, well, if you consider that there is no thermal energy loss, then you would know that the total initial energy that you start with has to equal the total final energy that you have. And that's what we saw earlier in the problem. We saw that the total initial gravitational potential energy equaled the total final kinetic energy. In other words, if you took the initial gravitational potential energy and you subtracted the final kinetic energy, you should get 0, right? And so here, though, we're not going to get 0. So if we take the initial potential energy and we subtract the final kinetic energy, we're going to have the change in energy due to, so this is the lost, quote unquote, lost thermal energy. Now, when we say that the energy is lost, this is why I'm writing it in quotations. It's not really missing. It just got converted to an unuseful form. So this thermal energy that's delta E, it's going to be EP1, which is mgh1, minus EK2, which is 1/2 mv2 squared. So mass is 2 kilograms. Let's see, G 9.81. H1 is 20 meters minus 1/2 m, which is 2 times V2 squared, so 15 squared. So 2 times 9.81 times 20 minus 0.5 times 2 times 15 squared. 167.4 joules. Okay, so that means 167.4 joules of energy was lost because of friction due to heat. And this is why so many engineering creations work on reducing heat. They work on reducing friction, any type of resistance. Okay, that's the energy lost, quote unquote lost, due to heat. Okay, back to the slides. Oh, by the way, in case you're wondering, the reason this number is a little different is because they are using 10 in the values. Excuse me. All right, our last, I guess, concept to look at with regards to conservation of energy, and the last, this is the second last slide we're going to look at with regard to section 2.3, is a pendulum. A pendulum is a really nice example of conservation of energy. Okay, so a pendulum is essentially this. Imagine you take a string and you tie a ball on the end of it, and you hold this string on one end with your finger, and you hold the ball on the other hand with your other hand. Okay, so you take that ball, lift it horizontally as shown in the picture, and then you just let it go. And when you let it go, it begins to swing back and forth, kind of like a child on a set of swings. Now, a green rectangle, kind of like you see here, this is going to represent the amount of potential energy in the system. When you see the rectangle turn red, it's going to be kinetic energy. And most of the time, it's going to be a combination of potential and kinetic energy. Sometimes there will be purely potential, sometimes it'll be purely kinetic. So pay really close attention to the animation to see when each of them happens. So when the pendulum first starts, it's at rest. The finger is holding it up, right? So right now, all of the energy is gravitational potential. There's no kinetic energy here. But this thing is going to swing down, right? The axis of rotation is right here. It's going to swing down and it's going to swing back up. Then it's going to swing down, swing back up, and keep on going like that forever. Oh, and you know what? Unfortunately, it looks like because my computer is running a bit slow, the animation doesn't look like it's working. Oh, that's really unfortunate. So you know what I'll do? Okay, so I'll put up the notes on the slides, and then I will explain it on the piece of paper so you can see. So there is constantly an exchange occurring between kinetic and potential energy. So let's go back to the slides. The page. So this is what's going on. You have a pendulum, and I'm going to draw it in a few different states. So initially, this thing is up here, right? And then after some time, it's going to swing down. It's going to be at the bottom. And then after some time, it's going to be over here. So this thing is swinging down and then swinging like this. And now it's at rest, but it wants to start coming down. And so it's going to be down here. And you know what? Let's just look at it here too. It's still on its way up. Okay. Now, when it starts here, this thing is swinging down. So this is the axis of rotation, right? This solid circle filled in. Right here, it has purely potential energy. When it swings down, this is when it's at its lowest height. So we would call this the reference height of h is equal to 0. So wherever this is its maximum height. And so at this point, it has its maximum potential energy. And since the only way to keep it there is to hold it, we know that the velocity at that point is 0. The velocity has to be 0 at the highest point, at its turning point. And as this thing starts to fall, it loses height, but it gains speed. And so that makes sense that when it's at the bottom, when it's at the lowest possible height, it would have the maximum speed. Therefore, the maximum kinetic energy. And that is since the potential energy is 0. Okay. And the potential energy is 0 since H is equal to 0. I hope that makes sense. Then this thing starts swinging back up. As it swings back up, it gains height, and so therefore it's gaining gravitational potential energy and it's losing speed. It slows down until it reaches the top again, at which point, at the maximum point before it turns around, the velocity is momentarily 0. You have your maximum potential energy again, but your kinetic energy is 0. Okay, so here we go again. This thing is swinging back down. We have our maximum kinetic energy again here, and we have 0 potential energy. Now, the reason I wanted to include this too is because here there's a combination of the two. It's not at its lowest point, so it does have some potential energy stored inside of it, so it's at some height h, but at the same time it has some non-zero velocity v. So here it has a combination of kinetic energy and potential energies. And in reality, most of the time, it's not at the highest point or the lowest point. Most of the time, it's swinging and it's at some point like this. So usually, the total energy that the pendulum has is a combination of kinetic and potential. But at specific points, specific special points, it either has only kinetic or only potential energy. So I apologize for that. It doesn't work here, unfortunately. But when you see the slides yourself, okay, when you download the PowerPoint, when it's posted, you will see the animation working. Okay. All right, so let's do this problem. Suppose the simple pendulum shown has a 1.25 kilogram bob connected to a string that is 0.475 meters long. Find the maximum velocity of the bob during its cycle. The bob, that's just the weird name for this thing on the end here. Okay, so sometimes it's called a plumb bob, and sometimes it's just called a bob. Okay, so let's not get into why that is, but let's just solve the problem. All right, so example. Okay, so we've got this, and we've got our pendulum, and this thing is going to swing down. So we don't really care about the mass of the string. We care about the mass of the bob. Okay, so that's the bob, and the mass of the bob is 1.25 kilograms. The rope is 0.475 meters long. We want to find the maximum velocity. Now, based on what we just inspected and analyzed, we saw that the maximum velocity occurs when it's vertical, so when it's at the minimum height. So when this thing swings, at some point it's going to be down here. And this is where Vmax is going to occur, just before it starts swinging back up. Okay, so Vmax occurs right here. And it occurs at the point where h equals 0. Now, if we call this reference line here, h is equal to 0, then what would this height be? What would the height up here be? Well, that height we can determine based on the length of the string. Since the string is 0.475 meters long, we can say that this height is 0.475 meters. All right. Now, the maximum speed means that you have maximum kinetic energy, but that kinetic energy came from the potential energy up here. So let's call this position 1. Let's call this position 2. I know that the total energy at position 1 equals the total energy at position 2. At position 1, it's purely potential energy, and at position 2, it's purely kinetic energy. So potential energy at 1 is mgh1, and kinetic energy at 2 is 1/2 mv2 squared. So the masses cancel, and what we're looking for here is v2. So Vmax is v2. All right, so if we rearrange this formula, we're going to get 2gh1 square root is equal to v2. So v2 is equal to the square root of 2 times 9.81 times h1. h1 is the height that it starts at. That's 0.475 meters. Excuse me. So 2 times 9.81 times 0.475. So yeah, so we can square root that. So v2 is 3.05 meters per second. And that is the maximum speed. So as this thing falls, it starts at a speed here of 0, right? Or we can call that v1 technically. That would be more accurate. So v1 is 0. And as this thing falls, it loses height, so h is decreasing, but the v is increasing. And it keeps increasing until it hits the biggest value down here. Okay, 3.05 meters per second. On its way up, that speed is going to decrease, 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 decrease until it hits 0 again at the maximum point, and it continues back and forth and back and forth. The reason the child on the swing eventually loses height, and the reason you have to keep pushing them on the swing, is due to the friction, the solid friction between the swing and the rods, and due to air resistance. If not for those two things, you could push them once and they would swing indefinitely. Okay, so that is it for section 2.3. Okay, so stay tuned next time for the next video.